Okay, and that is going to be through section 22.3 in the textbook if you want to go in and read into that. Okay, so the main physical property that we're going to be looking at is going to be boiling points. I want to start off this discussion of boiling points by kind of comparing amines to another functional group that you have seen earlier in this course. So I'll start off with an alcohol. So in this case, it's just an ethyl alcohol, otherwise known as ethanol. And I will compare it to the analogous amine. Very similar looking structures, only different by functional group. Okay. Now, when you're considering the context of the alcohol, the boiling point of ethanol is 78 degrees Celsius. When we're looking at this amine, this ethylamine, its boiling point is 17 degrees Celsius. Okay, so again, only different in functional group, but we have a quite significant difference in boiling point. And why is that? Well, the main difference is that within that functional group, we have different kinds of polarized bonds going on, okay? So in the case of an amine, we have these polar bonds. So you have a partial negative on nitrogen and a partial positive on hydrogen, which is great. That means that the fact that it's polar, it means that it can actually go in and participate quite well in hydrogen bonding. And we know that hydrogen bonding can actually go and essentially stabilize a mixture, or basically a group of those molecules through intermolecular interactions. Likewise, for the alcohol also has these polar bonds. However, because oxygen is more electronegative, it turns out that OH bonds are actually more polar than NH bonds. And because of that, alcohols can actually participate in hydrogen bonding much more readily than amines can. Okay, amines still participate in hydrogen bonding quite well, but the fact that you see much stronger hydrogen bonding with alcohols compared to amines can account for that significant difference that you see in the boiling point of two compounds that are only different by their functionalities. Okay, so to sum up what I just said, that OH bond is more polar than the NH bond. So because of that, OH is more capable of hydrogen bonding. And I will abbreviate hydrogen bonding as H bonding. Okay? So we've compared different functional groups. Let's look at different types of amines. So last class, we looked at the fact that there are different types of amines that are classified by their structure. Remember, we can have a primary amine. We can have a secondary amine. And we can have a tertiary amine. Okay, so we've talked a little bit about hydrogen bonding. Well, how can we apply hydrogen bonding here? Well, we can expect that hydrogen bonding will go and then essentially lower or increase the boiling point for an amine if it is capable of doing so. Okay, so kind of in the realm of the fact that a stronger hydrogen bond will increase the boiling point, which of these compounds would you expect to have the lower boiling points? Okay, so which of these would you expect to engage in less strong hydrogen bonding? Okay, so let's do a show of hands. 1, if you think it's a primary amine. 2, if you think it's a secondary. 3, if you think it's a tertiary. So which of these do you think has the lowest boiling point? Okay, seeing lots of 3s, very good. Yep, so 3 in this case would actually have the lowest boiling point. And how low would you ask? So if we look at the primary amine's boiling point is about 50 degrees Celsius. The secondary amine has a boiling point of about 34 degrees Celsius. And the tertiary amine has a boiling point of about 3 degrees Celsius. Okay, so you would actually expect that to be a gas at room temperature. All right, so we see that in either case over here, we have increased hydrogen bonding ability as we go to the left, in both the case of the alcohol versus amine, and in the case of primary, secondary, and tertiary amine. Okay, and the reason why these amines relative to each other have more or less hydrogen bonding ability is the fact that the primary amine has 2 NH bonds, so 2 of those polar bonds that can participate in hydrogen bonding. The secondary amine only has 1 NH bond, and the tertiary amine, well, in order to participate in any hydrogen bonding at all, you need to have at least 1 NH bond, okay, or at least for it to be a hydrogen bond donor. Okay, so if you just have a bottle of, or a solution of if you just have a bottle of a tertiary amine, that will not be able to engage in any hydrogen bonding. Okay, any questions about boiling point before we move on? Yes. Yes, so if you actually introduce some more structural some more functionality or some more structural features into it, you will start seeing like a little bit of more of inductive effects. That can actually be attributed to both hydrogen bonding, but also a little bit more of like a dipole-dipole interactions that can kind of help stabilize those molecules. Good question. Yes. Sorry, which amine? Oh, great question. So not all primary amines have the same boiling point, okay? And here we actually see that we have 1 more carbon than the amine on the top. So that 1 carbon will actually go and increase that boiling point quite a bit. All right, so let's go ahead and now move on to our next learning objective. Now we're gonna move a little bit away from talking about structure, and we're gonna now look more at some reactions. So learning objective 22C, we're gonna recall reactions that form CN bonds. Okay, and that is from section 22.6 in your textbook, okay? So we're gonna be looking at all the reactions that we have in our toolbox from 2301 and 2302 and see how we have been able to make amines up until this point. We'll start off with one of our main reactions from 2301, taking an alkyl halide. So we can use an alkyl halide as an electrophile and react it with some sort of a nucleophile. In this case, I'll use sodium azide as a nucleophile, and these two can engage in an SN2 reaction where that alkyl halide gets displaced, and you will now make a new alkyl azide, okay? And in case you're curious what the structure of that azide looks like, okay, so N3, it's actually just 3 nitrogens all bound to each other, and in this specific resonance structure, you have a positive and a negative charge on 2 separate nitrogens, accounting for an overall net neutral functionality, okay? So if you wanted to look at this reaction, you could look at sections 6.1 and 7.9 in your textbook. All right, let's go ahead and take another case. So let's say we have benzaldehyde. Okay, so remember benzaldehyde is just going to be a benzene ring that has an aldehyde bound to it. And this can actually act as a nucleophile in an EAS reaction. So let's say I wanted to go and then nitrate this using nitric acid and sulfuric acid, okay? Since we have our final exam coming up in just a few weeks, we'll do a little bit of review here. Remember, we have the ortho, meta, and para positions, okay? So given the fact that we have an aldehyde, we have ortho, meta, and para here, okay? Again, by a show of fingers, why don't you all predict where that nitro group would go? Okay, so 1 for ortho, 2 for meta, 3 for para. Ready? 3, 2, 1, go. Okay, so I'm seeing some 2s, some 3s. Okay, so let's recall. An aldehyde is an electron withdrawing. Okay, if it's an electron withdrawing groups will direct to the meta position. Okay, so here we would expect that we would nitrate at the 2 position. Okay, remember this can be a little tricky. So if you feel that you're still not quite sure about regional selectivity for these types of reactions, I would highly recommend going back and reviewing your EAS reactions from the start of the semester. Okay, I know it's been kind of a long journey since then, so make sure that you're kind of brushing up on the stuff that you may have not seen in a while. Let's take a terminal epoxide. That terminal epoxide can be reacted with some excess ammonia and water. And this is an SN2 reaction. And recall that if we're using a stronger electrophile, we can actually go and then break the epoxide. And with a strong electrophile, with a strong nucleophile, you will break the epoxide at the least hindered position. And then add your amine to the terminal position of that epoxide. Okay, so epoxide breaking is another way that you can make amines. That's from section 17.11 in your textbook. Okay, another way that we can potentially think about making amines, we can use benzaldehyde again, but this time I'm actually going to use benzaldehyde as an electrophile. And I can think about reacting benzaldehyde in the presence of perhaps methylamine. And methylamine is a primary amine, if you recall. So if you react a primary amine with an aldehyde, this will do a condensation reaction. And the product of this will be the imine, where you go and then you form a new carbon-nitrogen double bond. Okay, and whatever R group, in this case the methyl, will be bound to that nitrogen in the final product. Okay, so remember this is an imine, and this is from section 18.10, sorry. Okay, in a very similar fashion, but yielding a different product, I'll use acetaldehyde in this case, intentionally switching up my electrophile, and I'll react another amine with it. Okay, so instead of using a primary amine, I will now use a secondary amine. This will do a condensation reaction once again. All right, now, very, very important. If you're reacting a ketone or an aldehyde with a secondary amine, okay, you require an alpha proton. That is a proton that is bound to the carbon next to the carbonyl, not a proton on the carbonyl carbon itself. So we require that alpha proton, and the product that you end up forming here, will end up being an enamine. Again, the secondary amine has 2 R groups. And those 2 R groups will be bound to the nitrogen in the final product. Okay, now given that both of these reactions are condensation reactions, you release a small molecule, and in both cases, the small molecule that you end up releasing is going to be water. In the case of making your imine, the 2 protons will just come from your primary amine, but in the case of making your enamine, 1 proton will come from the amine, because the amine only has 1 proton that it can go and then transfer, and the other proton will come from the electrophile, from that alpha proton. Okay, so very, very important difference for considering where the protons come from in water for these 2 mechanisms. Okay, let's take a carboxylic acid derivative. So I'll use an acid chloride in this case. All right, so carboxylic acid derivatives are very useful for synthesizing amides, another really great way to form a carbon-nitrogen bond. All right, so we can use two equivalents of some sort of an amine. The amine has a requirement, however, and that requirement is that that amine needs to have at least one hydrogen atom on it, okay? So really, you can use ammonia, primary or secondary amine, but you cannot quite use a tertiary amine in order to be able to do this, okay? So doing this reaction will give you an amide. And then you will just go and then substitute that chloride with your amine minus one proton there, okay? Now this is going to be, again, an amide, and this is from sections 20.4, 20.5, and 20.10 in your textbook. So you may not realize it, but you have learned a lot of reactions so far in order to go and then make carbon-nitrogen bonds. Any questions? All right, so now let's learn about some new scenarios and see how we can apply this knowledge to maybe other compounds that we have seen before, but not quite considered the reactivity and the limitations of these reactions, okay? So we're gonna do this in learning objective 22D, which is the 4 Ps for the formation of mixtures of substituted amines from ammonia and alkyl halides through SN2. And that is from section 22.7 in your textbook. Okay, so let's say that you're a chemist and you're working in a lab and you want to take some sort of an alkyl halide and substitute something in order to go and make an amine, okay? The simplest way that you may think of doing this is by taking two equivalents of ammonia and some sort of an alkyl halide. And you may think, okay, great, I can do an SN2 reaction here. And the idea would be that I can go and then form a primary amine with a byproduct of my ammonium halide. Okay, so under the current understanding that you have of SN2 reactions, you would expect that this is a transformation that will likely happen, okay? You will take an ammonia, you will take your alkyl halide, we'll do a substitution, and this would be nice, handy dandy, okay? The reality is that yes, this happens, okay? So I'll kind of write expectation. Okay, so this is kind of an expectation or more so like a desire for what you may want to do with these reaction conditions. But the reality is you do get that product, but you actually end up with a mixture of products. And how exactly does that happen? Okay, well, we could think of our ammonia as being our nucleophile or our base in this reaction. And we could think of our alkyl halide as being our electrophile. So sure, yes, we do our desired SN2, but what actually ends up happening is that we will form our primary amine, but you will also end up taking that primary amine and doing another SN2 on some sort of electrophile that's left in solution in order to form the secondary amine. You think that secondary amine can also do an SN2? Sure it can. So you're actually going to end up with some tertiary amine as well. Do we think that tertiary amine can also do an SN2? Has a lone pair. Sure, why not? And you will actually also end up with a quaternary ammonium. Okay, so the whole point here is that you may just want to substitute once, but in reality, you're going to get a whole mixture of products that's going to bring your yield down significantly. Okay, so that means that these conditions to go and then form a primary amine are not good. Okay? Now, just to kind of recap how this would work, and I'm just going to show the reaction of ammonia with an alkyl halide. But you can imagine that the same reaction will also occur with the primary amine, the secondary amine, etc., to go and then form your more substituted product. All right, so the lone pair on your ammonia will go and then act as your nucleophile. It attacks the electrophile, break the weakest bonds. You end up forming an ammonium iodide intermediate. Okay, and the reason you need that second amine is that now you could take the lone pair on that amine and remove an NH bond in order to go and then make your benzylamine product, okay? So it's going to be that plus your ammonium iodide. And of course, that will go and then keep on reacting to get your mixture of primary, secondary, tertiary, and quaternary amines, or ammonium in the case of your quaternary. Okay? So this is not the best option. If you want only single alkylation. Okay, so now we have to think. We want to avoid this overreaction, okay? We have had cases in the class before where we have wanted to kind of avoid some sort of overreaction by maybe introducing some sort of extra synthetic steps or extra mechanistic steps, okay? It does involve extra steps, but it really, really helps out with our reactivity and helps us only get the product that we want. Does anyone remember what strategy we use in order to avoid overreaction? Good answer, but not quite. Dean Star Trap, we'd want to use that to remove water, and we're not quite forming water in this case. Yes. Ooh, changing the ratio of a reactant, the right reaction. reactant is an excellent answer. That could probably work. Maybe if you included a very large excess of your electrophile, you certainly could do that. But one such strategy that we thought of previously in the course is protecting groups. Okay, so I like the Dean-Stark answer a lot because you used the Dean-Stark trap to kind of go and install a protecting group onto a ketone or an aldehyde. So we want to recall how these protecting groups will prevent an overreaction or an undesired reaction, okay? So let's say that we had an aryl bromide that also had a ketone substituted, okay? And let's say I wanted to go and then take this and then make a Grignard reagent or an organomagnesium bromide. So I toss in some magnesium. Well, you probably will form that Grignard reagent. Cool, that's fine. But that Grignard reagent is actually going to go and then start finding some other ones of those ketones in solution. So essentially what will happen is that you see that your organometallic reagent will essentially just go in and react with itself, okay? And if it reacts with itself, that is bad for our desired reaction, okay? So the way that we kind of circumvented this issue was to add in some extra steps where we first had a protecting group, and then you add in magnesium. And then you can now form your organometallic reagent without any potential concern for reacting with some other ketone in solution, okay? So these conditions are better. Of course, the only caveat is that you have to add a protection and a deprotection step in order to get to the same product. But adding those extra steps are good if it means that the reaction will work. So you'd want to go in and take that route rather than just going and then adding magnesium to make your Grignard reagent without it, okay? Any questions? Okay, so now let's see how we can go and apply this understanding, okay? So apply how we can take a protecting group and prevent this overreaction, but now in the context of our amines, okay? Previously, we wanted to avoid molecules reacting with themselves. Now we want to introduce a case where we alkylate our amine or alkylate our nitrogen atom, but just once and have it stop there, okay? So learning objective 22E will show us how to do this. And these are the 4 Ps for the formation of primary amines from phthalimide, protected amines, and alkyl halides, followed by deprotection. Okay, and this is kind of a twofold learning objective also because you have the 4 Ps for the protection and you're also going to have the 2 Ps for the deprotection. And this can all be found in section 22.8 in the textbook. So the way that you can do this is through a reaction called the Gabriel amine synthesis. So let's see how this works. So we're gonna take this new molecule that you probably haven't seen before. Also contains a functional group that you're probably not quite familiar with. So this compound is called phthalimide. Contains a functional group called an imide, which you can imagine as just the nitrogen equivalent of an anhydride. And this phthalimide contains a quite acidic proton. So we can go and then introduce some sort of base, such as potassium hydroxide, and deprotonate. To go and then form your phthalimide salt. And then you will also have a byproduct of water in this case. Okay, so this phthalimide protects our nitrogen. And we could think of two ways how this protects the nitrogen, okay? The first way is that, well, compared to just ammonia, we now have nitrogen already being bound to two other carbons. So it's already a secondary nitrogen. So we don't have to worry about that further alkylation from the secondary nitrogen. So alkylating would take this from a secondary to a tertiary nitrogen. Great. But you're probably also thinking, wait, but can't tertiary nitrogens also alkylate further to make a quaternary? Well, the nice thing about these phthalimides is that that second lone pair, okay, is actually adjacent to two electron withdrawing groups. Okay, so you have electron withdrawing groups that are essentially stabilizing that lone pair through induction and through resonance. So those electron withdrawing groups will make the nitrogen less nucleophilic. And it'll just stop at the tertiary nitrogen. Okay, so how does this happen? So we can go and then take this phthalimide, the salt of it, and now we can go in and introduce our alkyl halide. All right, and then what happens here is that we can go and then take that lone pair on nitrogen. That lone pair on nitrogen acts as a nucleophile. It attacks the electrophile, break the weakest bond, and we once again just have an SN2 reaction. And the product ends up being the alkylated phthalimide. Okay, with a byproduct of just your potassium halide. Okay, great. So now we have gone and successfully alkylated our phthalimide over here. But of course, because that phthalimide is acting as a protecting group, we do need to add that extra synthetic step of deprotecting. Okay? So in order to deprotect this, right, and then this is just going to be a 2p. You're going to go and then take that phthalimide, and you're going to introduce a reagent called hydrazine. That's NH2NH2. And you're going to use ethanol solvent, which will actually just go in and act as a proton source. And you end up getting out your primary amide. And the byproduct actually goes and kind of traps the rest of that hydrazine. And forms what essentially looks like a diamide with a nitrogen-nitrogen bond. Okay? Now this reaction is great because, as I mentioned, we have solved our issue of whether or not we just get our primary amine or a mixture, and we get our primary amine only here. Okay, so very, very useful in synthesis if you just want to stay at that primary amine. Any questions about this reaction? Okay, so if you think of it, the overall reaction is just a deprotonation followed by an SN2, and then finally you just deprotect. Okay, so some more steps, but these are all things that you have seen in the class already. How are we feeling? You ready to do a chime in based off what we just talked about? Oop. Sorry, don't know why. Gotta love do a push. Okay, so here is our chime-in question. What is the best set of conditions to make the product shown? So go ahead and think about this, and then we will go and then talk about what we think the answer is as a group. We have about 20 more seconds before you go over the answer. All right, so let's see how we did. Okay, so looks like we have most people choosing B, and we have some people choosing A. Okay, so yep, I totally get it. I do like the fact that a lot of us are kind of leaning towards using a phthalimide, which is great. The question is, what steps are necessary in order for us to be able to actually do this? Okay, so really, really like this distribution of answers over here. So let's go ahead and figure out what our most desired conditions are in order to go in and do this reaction. Okay, so let's go and take a look. So again, we're starting with a primary alkyl halide. And we want to use some conditions to make a primary amine. Okay, so answer choice A over here tells us that we should start with just phthalimide. Okay, which I like, the fact that we're starting with phthalimide over here. And recall, we just go and then add in our potassium hydroxide, which goes and then deprotonates that phthalimide. And then now we add in our alkyl halide from our starting material. And we end up with our alkylated phthalimide. Okay, so really awesome thinking over here. However, because we did discuss that the phthalimide was a protecting group, if you don't deprotect the phthalimide, it's actually just going to go and then stay on your compound. Okay, so the conditions with answer choice A would have you stopping here. And to get that primary amine, you cannot stop here. Okay, you do need to add in that extra step. Okay, and what answer choice B does is that it actually omits that first step. That first step already has the phthalimide salt. Okay, so it was just preformed at some point before. And then it adds in the alkyl halide, which is great. But then answer choice B also has that deprotection step. Okay, so again, hydrazine and ethanol. And that will go and then end up giving you your desired amine product. Okay, so this is what you get from answer choice B. And including that deprotection step is correct. Okay, answer choice C. Answer choice C used 2 equivalents of ammonia, and we just discussed that if you just use ammonia unprotected, what's going to happen is that you're going to end up with a mixture of overalkylated products. Okay, and then finally for answer choice D, we start by forming our organometallic, our Grignard reagent. But what you're doing is that you're taking that organometallic and then you're adding in ammonia, which is an acid, which makes this not compatible. Okay, so that means that our correct answer is answer choice B. Okay, questions about this? All right, and then our final learning objective for today is going to be learning objective 22F. Which is the 2 Ps for the formation of amines from azides, nitriles, amides, and nitro groups through reduction. And that is from section 22.9 in the textbook. Okay, so these are all other ways that you can actually go and then make amines from functional groups that you may be familiar with. Okay, so azides, remember an alkyl azide, that's a group that we saw in class earlier today. You can actually go and reduce an azide to the alkyl amine. Okay, and you have 2 possible sets of conditions to do this. You can either use your catalytic hydrogenation conditions, so with hydrogen and palladium, or using a hydride reductant such as lithium aluminum hydride, followed by water. Okay, so this is a really great way in order to go and then take an azide and reduce it in order to go and then make a primary amine. We can also take a nitrile. All right, so that's going to be RC triple bond to N. And actually using the same conditions, so either hydrogen and palladium or lithium aluminum hydride and water, we can go and essentially completely reduce that triple bond to a single bond, adding hydrogens all across. Again, another way to form an amine in this case. Okay, we can look at nitro groups. Actually, I'll do amides first. Okay, so let's say that we had an amide, and it could be a primary, secondary, or a tertiary amide. Okay, here we can use a hydride reductant, not hydrogen with palladium. What will happen is that the carbonyl will get entirely reduced. Okay, just leaving a CH2 there in the middle. And then finally, for nitro groups, okay, the only nitro groups we've really talked about in class are aronitro groups. And you can reduce those by using hydrogen and palladium, but not a hydride reductant. And doing so, we'll go and then give you a phenylamine. So in this case, this is an aniline. Okay, so to summarize our reductions, so these reductions will add in equivalents of hydrogen. And you could do so either by adding in hydrogen gas, or by adding in a hydride reagent, such as lithium aluminum hydride, or by doing an acid workup, okay? Very similar to reductions that you've seen in the class before, but now you can apply them to amines, okay? Any questions? All right, thanks for joining me today for this lecture. Have a great weekend, and remember to study for your exam on Wednesday. Good